very much for the organizers for the invitation. I've been really enjoying this conference, and somehow, spaces and tensor categories and their interactions is kind of, the kind of thing I think about on a daily basis. So really, it's great to be here. So I promised some variations. Variations require a theme. Let's start with our theme. I mean, I'm going to be pretty quick because this is has been largely covered by David Reuter on Tuesday. But my starting point is going to be the notion of Witt equivalence, introduced by Davidov, Uyghur, Nikšić, and Ostrich. So very quickly, recall that it's fresh into our minds that two non-degenerate related fusion categories, A and B, well, you all know what I'm going to write it anyways. If there exists the fusion category C and a braided monoidal equivalence between the tensor product or the Deligne tensor product of A and B with the Drinfeld center of C. That's the notion of Witt equivalence as originally introduced. And correspondingly, there is a group, so quantum Witt group. And I'm going to say quantum. People have not always used quantum this week. Well, notice maybe for now, there's a little subscript step. I'm not really going to explain today, but there are going to be other subscripts. And this group is obtained by taking the quotient of the commutative monoid of non-degenerate braided fusion categories modulo maybe one quick comment. Of course, it's not entirely clear from this definition that Witt equivalence actually is an equivalence relation. It should work a little bit, but that's what Davidov, Uyghur, Nikšić, and Ostrich did. Okay, and then as kind of first slight variation on this theme, we actually saw on Tuesday and maybe already on Monday for those of you that were already here on Monday that this group actually arises as the group of connected components in a space. And the natural way to present this space is by, is as sitting inside some higher symmetric monoidal category. So Rocher, Jordan, and Snyder constructed for us. A Morita 4 category of braided fusion 1 categories. So that I guess objects are braided. I mean, you can keep the multi or not depending on taste. And maybe let me write at least once what the one morphisms are in some amount of details. So one morphisms. So from A to B, well, they're almost going to look like Witt equivalences, but not quite. So they are given by multi-fusion categories. C, equipped with a braided functor from A times B rev into its center. But now I'm not requiring that this is an equivalence. And then, then you can look into that paper to see what the higher morphisms are. I'm not going to spell this out. And then in, as David recalled on Tuesday, in follow-up work with Safronov, they actually showed that, oh, I did not give it a name, this is terrible, so wait. This is more to SEP. The two refers to the fact that it's a multi-category of E2 algebras, meaning braided monoidal categories. So the Picard group of more to SEP, by which I really mean a group of equivalence classes of invertible objects up to equivalence is isomorphic to the quantum Witt group. Morphic. And in particular, as promised, realizes the Witt group as a set of group of connected component of this space. By this space, how do you get a space from a higher monoidal category? Well, you keep only the invertible things. This will be my notation for invertible objects, then invertible morphisms. But really, this is a spectrum of or higher abelian group. Think of it as a space. Okay, so that's my starting point. And then I promised some variations. So really what I would like to do is think about how to make this non-semi-simple. And here, essentially, the problematic is going to be that there are essentially two things you can do, and they do not obviously agree. I don't actually know whether, I don't even know whether I should expect that they agree or not, but there are essentially two things you can do. So what are the two things you can do? Well, one thing that you can do is actually follow the higher category theory. You can follow, where the higher category theory leads you. And that's really what Brochet, Jordan, Snyder, and Safronov did, because really they did not only construct, they did not only look at this this Morita 4 category in the case when you have finite semi-simple tensor categories, but they constructed something more general. And if you're familiar enough with higher Morita categories and higher Morita categories of tensor categories, well, you know that Douglas, Schirmer, Priest, and Snyder constructed a Morita 3 category of finite tensor categories. So naively, you might expect that, well, maybe there is a Morita 4 category of finite braided tensor categories. And that would be kind of the obvious thing to take, and then you can just run this. Well, this doesn't work. So instead, you have to weaken a little bit the notion of a tensor category that you use.
Very good. Why it does?
Why it doesn't work? Yes. The relative Deligne tensor product just fails to doesn't act. If you take, you can build things like this. Well, this is a finite braided tensor category. These are two finite tensor categories, but this whole thing is actually not a finite tensor category. It's still finite, still monoidal, but somehow not all objects have duals. But yes, essentially that's the thing that I will explain. But yes, so in order to fix this problem, we need to weaken our definition of a tensor category. Well, by tensor category, I'm using the Ettinghoff, Gelakin, Nikšić, Ostrich definition. Maybe some other people have used a different one. Definition. Yes, I'm going to attribute to Brochet, Jordan, Snyder. Although I'm not going to use that terminology, so for me, a finite pre-tensor category is a finite monoidal category, so finite in the sense of EGNO. but I'm only going to ask that the tensor product is right exact. And I'm only going to ask that projective objects have duals and such that.
Left and right?
Yes.
Not asking Grothendieck-Peltier.
Pardon?
You're not asking Grothendieck-Peltier, which would be the.
No, I am not. And you may know this as CP rigidity. But somehow my list of adjectives is already too long, so if I could condense it a little bit.
What is CP?
Compact projective, because somehow yes, I mean, maybe I should point this out. In Brochet, Jordan, and Snyder, they don't actually restrict to categories that are finite, but I do because all of the things I'm going to consider are finite. So in my case, you can actually drop the compact, and then it's just something about.
Just because everything is compact.
Yes, just because everything's compact. So, I think I want to come on board management. Oh, well, I guess it's a theorem of the same people, so I might as well just use this again. And it turns out that if instead of trying to take finite braided tensor categories as your object, but you instead take, let's maybe braided finite pre-tensor categories. And well, similarly for your one morphisms, instead of considering multi-fusion, you take finite pre-tensor categories. Well, I guess now it has a different name.
So you reserve the terminology of a tensor category for the case for all objects.
Yes, absolutely. Yeah. Sorry, this was implicit in my. Yes, that's a good question. Thanks, Paul. Yes, so it is a theorem by the same people that there is actually a Morita 4 category of finite braided tensor categories, and then one morphisms, maybe you can call them central finite pre-tensor categories. And maybe because this is of interest to some people, let me just quickly mention. So what's really nice about this 4 category is that it's actually 3 dualizable, whereas the previous one was fully dualizable.
Sorry. This question is you drop the multi, so you're restricting to unit.
Right. No. So yes. You can look at this definition. I've assumed nothing of the Molitor unit.
And second thing, you assume that it's clear why the difference center of a pretensor category is a pretensor category.
I mean, it follows from their work. Yes, it is true. It is true, but it's something they show. I mean, I don't think they state it explicitly. Maybe they do. But yes, it's definitely something that is not. Okay. And then, we can try to, they succeeded in showing that you actually have a good supply of invertible objects in this Morita 4 category. So, namely, it's a theorem of Brochet, Jordan, Snyder, Safronov that every non-degenerate finite braided tensor category is an invertible object in this point, invertible object of more to
Symmetric center is trivial, or
yes, means symmetrical vector spaces. And in particular, it implies that the monadal unit is simple, which is why I don't need to write it. Maybe one one quick word on the proof. This relies very crucially on Shimizu's characterizations of non-degeneracy. And well, we have a symmetric monoidal 4 category. Our desired categories of interest are invertible objects in it, constructed a promising space. So, yes, maybe tentative definition. So, I0 of mod 2, 3 is a good candidate for a non-semi-simple version of the quantum Witt group. And the advantage of this perspective is like, well, it's very natural from a higher category theoretic perspective. And also this really just builds it as a space already. I don't have to think about how to make this in space. I mean, somehow, by definition, like this is connected components of a space. Oh. This was the third variation. Yes, okay.
Group is automatic because you take invertible objects, right?
Yes. Well, and because it's a symmetric monoidal higher category.
All obvious how to decide if like if I have two actually tensor rated objects, you know, sort of two objects in this which I've realized is
We're
tensor.
doing Andre. Answer is no.
Okay.
And answer is also yes, that's where I'm going.
You gave a theorem which gives some examples, but
Well, not in anyways.
no, but yeah, it's not three, because you have pretensor categories. Are there any other invertible Riemann pretensor categories which are not?
Well, I do want to give my I would prefer to be able to give my talk, and
Sorry, yeah.
I mean this course will be in discussion session.
Sorry.
Okay, so variation number 2.
Excellent.
So the variation and the variation number 2 is, well, in the first definition that I very unfortunately had to erase, you can actually just drop the finite semi-simplicity assumption. And this is something that Mitsu and Yadav did. So you can say that to non-degenerate finite braided tensor categories A and B are equivalent. Again, really know where I'm going, but if there exists a finite tensor category C and a braided equivalence between the tensor product of A and B with the opposite braiding and the Greenfeld center of C. Some work goes into showing that this indeed defines an equivalence relation, but it does.
So those in general abstractions doing position.
I'm not and well, I will tell you that it's fine if you actually want me to give you detail that we can to ask after the talk.
I'm just trying to confirm the statement. The statement is that sort of that abstraction doesn't occur in these sort of when
I
everything.
am going there. We are going there. Yes.
Okay.
Give me 5 minutes, and in 5 minutes you're not happy, you're allowed to grill me until you're happy.
Really, in the statement.
Currently there's no statement. I'm just saying there's something a priori different you can do that also produces a group. Problem is it's not evidently part of any kind of space, but they show that we have a group. And then you can define Witt thin quotient of one to generate. Tensor categories by the relation of this. I guess, yes, I should emphasize. This is somehow very much in the spirit of Davidoff, Migo, Nikšić, Ostrich.
The using like Lagrangian algebras or something. Yeah.
Yes. Yeah. I mean, almost exactly what you would have, exactly what you would have done. Almost exactly what
How do you
is
know?
in your paper. I mean, it's a little bit more subtle, but like not massive. But that here, the problem, maybe I should end with one observation. So observation one is that with this definition, and if you know a little bit about finite weighted tensor categories, there is actually a very natural group homomorphism, which is in fact an inclusion. It is inclusion of the Witt group of non-degenerate weighted fusion categories into that of not necessarily semi-simple finite weighted fusion categories. That's a good feature of this construction. And then a very natural question, which I think many of us are interested in, I would attribute it to some people, but I think at least 3 different groups of people have some variant of this question. So I will, anyway, it's not a question I am posing. I guess it's a question the community has agreed on. It's a good question. What is the co-kernel?
How hard is it to see that the obvious map was an inclusion?
It's because the Drinfeld center of, well, at least in characteristic 0, I don't think characteristic 0, the center of a fusion category is still semi-simple.
The wrong-
With the center of
That the other way around.
Sorry, the other way around.
Yeah.
Sorry. If the center is finite semi-simple, then the category which it is the center is also semi-simple.
Is it a written statement? So
And that's right. I know that's the same question. Is that an easy? Yeah, like I've never done that exercise.
You used to forget
Yeah.
the counter from the center to A.
It's dominant, and you know that
Use the left counter.
it's in EGNO. Some variant of this is in EGNO. Yes.
This question, I thought it isn't,
It's too long.
the stronger question would be, is that an equivalence, right?
Well, I mean, the thing is, I'm not confident that, well, maybe that this is not an equivalence, but I also don't know. I don't really have any evidence either way. So the question I can ask that doesn't actually make me tell you anything about what I believe is this. And then you can make your own conclusions. Okay. The issue, so I guess I'm kind of running late to make Theo happy about the space bit of this, but we're getting there. Maybe the issue with this definition is that, well, what space is it associated with? Well, it turns out there is a space, but you have to somehow do something somewhat artificial. So maybe I want to, well, yeah, let's just reuse this as many times as I can. So what you have to do is, well, think about what failed in this relative Billion tensor product example. And really what failed is, or what can fail, is the following. So I assume I have a finite weighted tensor category. And I have C, I guess I'm just going to say it, a central finite tensor category, by which I mean C is a finite tensor category and it comes equipped with a braided functor from A to its Drinfeld center. So this is the kind of thing that shows up as the one morphisms in this 4 category. Well, I'm going to say that it is faithfully flat if the functor is fully faithful.
Not into C, but just into Z.
Yes. Well, it turns out, yes, I mean, it turns out if you read your original paper, the only thing that you use is actually that it's fully faithful into the center. You never actually need to be fully faithful down to C. In fact, in practice, it's actually necessary to know that it's enough to just go to the center. And well, with this, I can modify this theorem. Well, I guess it's not quite Brochet, Jordan, Snyder, so maybe. And get rid of the pre. I need to change my subscript. I mean, I don't have a terribly good name for this. If you have a better suggestion, feel free to give it to me. But now these need to be faithfully flat. And really the statement at this point, which, well, how late I am on my schedule. I mean, I'm late, but not terribly late. So maybe I will say, give one ingredient as to why you should believe that this statement might be correct. So proof. Need to show that one morphisms compose. And really the thing that's the most difficult is to show that they remained finite tensor categories when you compose them. The main difficulty. To address, I guess, the rigidity of objects is a tensor property. And this follows from, well, some elaboration in this lemma. I mean, this lemma in itself is not quite enough, but it's, at least I view it as the main key ingredient. There are a few other things that you should glean from Shimizu and Yadav, which is that if you have a fully faithful tensor functor between finite tensor categories, then it preserves exact algebras. I realize that this takes people that are not familiar with EGNO, but to the people who are familiar with EGNO and therefore might have some concern about the validity of this statement, well, that should go at least some non-trivial way towards making you happy and making you believe that this statement is plausible. Why should you believe that the lemma is actually accurate? Well, I would say that it's pretty much a standard EGNO style argument. But you have to use some non-trivial observation because this is somewhat of a non-trivial statement. You have to use this recent result of Coulombier, Stroinsky, and Zollman that exact algebras are the same thing as finite semi-simple algebras. Plus, Coulombier. I think the accent goes like this. Someone correct me if that's wrong. Plus, Coulombier's algebras. Oh, something that's like this. The point is that it's easy to show that fully faithful tensor functors preserve finite semi-simple algebras, and then you just go back and forth.
Sorry, what is finite semi-simple?
The Jacobson radical is trivial.
There, in your, you also. Tell me what the condition is. I just want to know if it exists.
Yes.
Like the faithful flatness type.
I mean, yes.
What is Jacob's radical? The Jacob's radical with most ideal.
What about ideal?
One-sided. Jacob's radical is usually the intersection of one side maximum ideals. So what is the definition of Jacob's radical?
Literally what you said is like,
Oh, just like that.
okay. Maybe some piece of warning. This is, well, okay. Let me read the benefit of what we just did. Actually not very hard to show again. So using this, I guess the invertibility result of Brochet, Jordan, Snyder, Safronov, that was inevitable. That the Picard group of this thing we have just constructed actually covers this non-semi-simple Witt group of Shimizu and Yadav. So at least we've achieved that. A piece of warning, though, is that from a higher categorical perspective, this is, I mean, it works, but it's pretty artificial. I mean, somehow this Morita 4 category has really garbage higher generalizability properties. I mean, somehow the invertible objects, I mean, you're fine, but somehow everything else goes out of the window. It's obviously garbage, but somehow. So that's why I'm saying from a higher categorical perspective, it's kind of a really weird thing to consider. I mean, somehow you would only consider it if you're trying to exhibit this as, you know,
It's kind of garbage. It's too much.
So, Thibaut, the Shimizu out of finite width,
It's all too much.
that one on the right, they never had any kind of faithfully flat condition in there. Like they weren't even thinking about the whole.
no, but it's because they only have equivalences, and equivalences automatically satisfy this space over. Okay, thank you. I am also introducing it as a bit of foreshadowing for later. Yes, David.
So do you also get the equivalent, take the original one you've written down there and just go to the subgroup of those objects that have a?
I don't know. So this is the question I'm. Can I go right to the question? If my question is not the question you had, you can ask a question. But yes, so the question, which is a variant of a question that was asked by Brochet, Jordan, Snyder, Safronov, is now, well, I guess the question I want to ask is what is the kernel of the map from, well, I guess we want this with fin, which is the same thing as I0 of mod 2 briefly flat to I0 of mod 2 3. And if you're really, really brave, you can ask about the co-kernel, but I am not that brave.
Didn't you just answer this question? You said that every equivalence is automatically faithfully flat. Every equivalence in the previous category is automatically.
The problem is that in this thing, C is allowed to be pretensor, whereas in this thing it is not. So I do not know whether if you take, I do not know if there exists finite pretensor categories whose Drinfeld center is still finite, is finite tensor.
You did not say that every equivalence is automatically finite tensor to sort of representing.
Yeah. That I have, I mean, from talking to people that have thought about finite pretensor categories more than I have, it seems highly unlikely that this is a true statement, but I don't know any counterexample either. That's again, for Ingo's, is also why this is a question and not a conjectural. It's being trivial. Okay. Any other question, comment?
Another question.
Yes.
If you compose it with the map from the classical Witt group, is it possible? Like, is it clear? Do you know what this kernel of that is, or is it also not clear? So, if you're the center of a pretensor, a finite pretensor category, and you're semi-simple, does that also imply that your finite pretensor category was semi-simple, like the argument that should have happened before?
No, because you're failing, it's no longer dominant. Like the thing that fails when you go here is that you kind of lose dominance of the map from the center to the thing down. I have no idea. Yeah, it could be whatever, I have no idea. Very good question. This is mostly all of the hard computational things are mostly questions that are left for brave members of the audience. Okay. So kind of explained how to go from the semi-simple version of the Witt group to, well, some take prefer non-semi-simple versions. Something else that you can do, okay, at this point is getting too clever, so I guess you go. Something else that you are very naturally led to, I mean, in fact, this showed up in David's talk, and this goes back to ideas of Davidov, Lipschitz, and Ostrich, is that, well, there are also many interesting other finite braided tensor categories, and why don't we think about them as well? But I mean, there's no reason not to think about them. So really, from now on, hey, I want it to be a perfect field. You are encouraged to think of a perfect field that has a positive characteristic. Right. And if I want to try and organize, other finite braided tensor categories into a group, well, maybe you go and look back at, I don't know, like your course on algebra, maybe your course on Breuer groups or something like that, and what you realize is that, well, really, you need some kind of enrichment. I need to actually fix the symmetric centers of these finite braided tensor categories. So E going to be any finite symmetric tensor category. And the notion that we are going to be interested in is the following. So an E enriched finite braided can be pretensor, it can be actually tensor. The definition is valid for both. Pretensor category B. Well, going to be a finite braided pretensor category. And then you can all guess what's coming. Well, equipped with a symmetric tensor functor from E to the symmetric center of B. Cool. And again, I mean, really for emphasis, this goes back to ideas of Davidov, Lipschitz, and Ostrich. And in David's talk, well, really he considered the case when E is super vector spaces. But you can take something else. In particular, if you like positive characteristic, I mean, maybe you can take the Linde categories that Sarah mentioned yesterday. A little observation is that, well, by these things, I mean at least the pretensor ones can very naturally be assembled into a symmetric monoidal 4 category, which is just something you can get from Brochet, Jordan, Snyder. There it is. A symmetric monoidal 4 category. Small 2, 3, E, for which objects are enriched finite braided tensor categories. Pretensor, there's a pre. And one morphisms are E enriched central finite pretensor categories. And again, if we follow our higher categorical nodes, well, we maybe suspect that some E-enriched finite braided tensor categories, because those are the ones that I really understand, are going to give us invertible objects in this guy. And ask which ones? Well, really is something that Davidov, Davidov, Nikšić, and Ostrich would have been able to at least guess, if not maybe completely prove. The definition, an E-enriched finite braided, I guess, and E pre-tensor, but I'm only going to use this for tensor categories. Is non-degenerate, or maybe E non-degenerate. If the, that should be, have a name, so it has to be F. If F is an equivalence.
When your notion of pretensor, you hide simple unit.
Notion of pretensor I had simple. No. Oh, okay, yes, good point. So if you take E to be vector spaces, well, this actually forces E to have simple unit, right? Because the symmetric center is always going to contain all the summons of the simple unit. If there's more than one, well, this cannot be an equivalence. But yes, this is why I can be sloppy with that, is because I've always.
You call it the enriched, but that is usually something else, but you have like over E, but because of the.
You don't want to call it over E because this would make some people in this audience relatively upset. And I also.
Yeah, but they will still.
And if I call them under E, you would not like
Yeah,
that.
the question is, will we be really enriched? Will have.
Yes, you can actually.
Reaction forms because of.
Yes, by results of Lavnik, Pennies, and Morrison. I think it's the right paper. Anyway, they have a series of 3 papers on using the result of one of the 3 papers. You can actually construct enriched. But I mean, I guess the thing is, if you actually want to do this enriched, I don't really exactly.
It's like more like tensored and enriched, but I think it's.
Yes, I mean, in principle, it should be formal, but I'm not. You should ask, I guess you should ask David or Marcus. They would probably know. Okay. And then what you can show
Thibaut, can you hear me?
is that non-degenerate, E-enriched by braided categories are indeed invertible objects in this guy.
The last check, how much dualizability does this category have? The 3?
Because everything is finite pretensor. This is Jordan Snyder. You don't even have to think, you just have to read and realize you have nothing to do.
Hi, Thibaut, can you hear me?
Yes.
Could I ask you a question about this notion? So there's 2 things I could think that this notion is equivalent to. One would be to consider E2 algebras in where you change your base category to be like the category of E modules.
Yes.
And the other would be to take like the 5 category of symmetric tensor categories and take endomorphisms of E there. Which one is your notion?
The first one, because in the second one, I think you would need 2 functors from E probably.
Okay, so this is the first
Yes,
notion. Okay.
yeah. I mean, the way you would build it is you would start by taking E2 algebras in modules for E in PL.
Okay. Thank you.
And just to clarify, in this theorem, you really need tensor, not pretensor.
Yes, I only know how to prove this for tensor. Yes, that also upset you last time you went with. I can tell you, I didn't know this is
Afterwards, it's okay. I just.
Invertible. In more 2, 3. And the proof, well, you have to use using invertibility criterion. Criterion developed from BTSS, from Brashear, Jordan, Snyder, Safronov. And then, because we have that, it essentially reduces to an E-enriched version of Schmitz's characterizations of non-degeneracy. So then, enriched. And somehow that's essentially where I need the finite tensors, because Shimizu's result really gives us finite. Okay, what am I doing in goals? Put this here or not? Yes. Yeah. I'm running out of time, but I definitely ought to mention that in a different context, Pinera obtained a related result. But more precisely, what Patrick considered is the case when E is representations of finite semi-simple algebraic group. So some are completely orthogonal because he was interested in like very big tensor categories, where I'm only interested in ones that are finite. But there's also similarly some kind of E-enriched version of Schmitz's characterizations of. Okay. It's hard because I definitely don't have the time to do all the things I wanted to do, so I have to pick which one. Okay, I mean, let me. This finishes this gives a higher categorical perspective on, I guess, an E-enriched version of the Witt group, right? So we have, I guess, a proposal that we can take a zero of more E as a non-semi-simple E-enriched Witt group. But somehow this is, this hopefully makes you relatively happy if you're a higher category theorist. This probably doesn't make you so happy if you're a tensor category theorist. So you can do something kind of much more concrete. But instead of giving you the concrete thing, I'm going to cheat, and I'm going to actually just modify this along the same lines as I modified the previous definition and get back the concrete thing. And
Extremely happy pre-tensor theorist. It would make a pre-tensor theorist extremely happy.
I mean, I don't know many of them, but I've been told they exist. So what we need to do, I mean, you can all guess. Where's my proposition here? So if I want to have a version of this where I actually have finite tensor categories showing up, well, I need to impose some faithful flatness conditions. But now I also need to impose it at the level of objects.
Maybe I can remark that a pre-tensor theorist is also known as an algebraic geometer.
Or a representation theorist.
But it's a not fine.
Wait for. And this gives you another proposal. So maybe we could write Witt bin of E as the group of the components of this more two faithful flat E-enriched finite braided tensor categories. And I mean, again, you can ask the same questions as before. There's a map from this to that. I have no idea what that map is. Your guess is as good, if not better than mine. And well, I am out of time, so I will stop here.